Oh, hi friends. Uh, this is the third class in simple harmonic oscillator. Okay. Before watching this, before going through this class, you have to watch previous two classes. Okay. This is then only you will get the continuity. And in this class, we know the property of creation operator. There is a dagger operating on n will give under root n plus 1 get n plus 1. So by using this equation, we can find out a dagger 0. That is equal to here n equal to 0. So 0 plus 1 under root 0 plus 1 is 1 and get 0 plus 1 is 1. And then a dagger 1. A dagger 1 is 1 plus under root 1 plus 1 is under root 2 get 2 and so on. Okay. And then a dagger 1 means a dagger into actually this ket 1 is a dagger 0. So we can write instead of ket 1 a dagger 0 and that is equal to a dagger square ket 0. Okay, and from this portion we got a dagger 1 equal to under root 2 ket 2. Okay, from that we will get ket 2 equal to a dagger square over under root 2 ket 0. In terms of ket 0 we got this one. So here we have written ket 1 is also in terms of ket 0 and our intention is we need to write all the number kets in terms of this ket 0. Okay, for that next step is a dagger 2 equal to a dagger, we know what is ket 2 from here. Okay, ket 2 is a dagger square over under root 2 ket 0. Okay, and that is equal to a dagger square over under root 2 ket 0, and in left side from this equation we can take a dagger 2 equal to under root 3 ket 3. Okay, from that we can solve ket 3 equal to a dagger cube over under root 6 ket 0. Okay, so let me conclude this one. We can write ket 1 as a dagger 0. Okay, from here ket 1 as a dagger 0, and from here ket 2 as a dagger square over under root 2 ket 0. Okay, and ket 3 equal to, from this equation, ket 3 equal to a dagger cube over under root 3 under root 6. 6 means 3 factorial. Okay, that means I need to generalize this. I need to make one equation. I need to make one general equation here. For that I am writing this 6 as 3 factorial. Okay, so we can make a general equation from this one. That is ket n equal to a dagger whole raised to n over under root n factorial ket 0. Okay, so in this way we can write any numerical ket in terms of ket 0. Okay, we know these two equations. A operates on n and we will get under root n minus 1. If a dagger operates on n, we will get under root n plus 1 get n plus 1. Okay, and if this operator is in the form of matrix, then we will find the matrix element like this. Okay, n dash a n, that is equal to, if a operates on n, we will get that is equal to under root n minus 1. That's why here under root n into get n minus 1. So we can take this under root n outside and we will get the inner product of n dash n minus 1. Okay, this means that is equal to under root n delta n dash n minus 1. That means if n dash is equal to n minus 1, we will get n dash a n equal to under root n, and if n dash is not equal to n minus 1, then we will get this is equal to 0. Okay, similarly the matrix elements of a dagger also we can define like this, that is equal to under root n plus 1 delta n dash n plus 1. Okay, next we defined two operators. This is our creation operator and this is our annihilation operator. Okay, and we studied by this term. And the annihilation operator is under root m omega over 2h cross x plus ip over m omega. And our creation operator is under root m omega over 2h plus x minus ip over m omega. Okay. From this two definitions, from these two terms, in both of these operators, x and p are included. Okay, so if we add this one, and we manipulate, we should get as x equal to under root h cross over 2 m omega a plus a dagger, and we will get, if you're subtracting this equation and manipulating, we will get p equal to I under root mh cross omega over 2 a dagger minus a. Okay, and next, this is an operator, this is also an operator. So we are finding the matrix elements of these two operators. Okay, matrix elements we are finding like bra n dash x get n equal to n dash this x is operator x is under root h cross over 2 m omega a plus a dagger into get n. Okay, so this we can take outside under root h cross over 2 m omega, and inside this bracket n dash a n dash a dagger n, and that is equal to under root h cross over 2 m omega, and if a operates on n, that we will get a operates on n, we will get under root n get n minus 1. So we will take this under root n outside, and we will get the inner product of n dash and n minus 1. Okay, plus the next term, we will get like this: a dagger operates on n. If a dagger operates on n, we will get under root n get n plus 1. Okay, so here we got n dash, the inner product of n dash n plus 1. That is equal to under root h cross over 2 m omega under root n. We can define it as delta n dash n minus 1. Okay, plus under root n plus 1 delta n dash n plus 1. That means if n dash equal to n minus 1, this will become under root n, or if n dash is not equal to n minus 1, this will become 0. This term will become 0. And here also it's like that. If n dash equal to n plus 1, this term will be under root n plus 1, and if n dash is not equal to n plus 1, this term is equal to 0. Okay. Let me put this equation as equation 15 and this as equation 16, and this one equation 17, and this one equation 18. Okay, the 17 and 18 are important equations, and this is equation 19. Okay, equation 19. And next, we'll find n dash pn, that is equal to I under root mh cross omega over 2 n dash minus a plus a dagger n. Okay, and finally we will get that is equal to I under root mh cross omega over 2 minus under root n delta n dash n minus 1 plus under root n plus 1 delta n dash n plus 1. Okay, this is the equation. This is equation 20. Okay, so let me write these four equations together. Okay, first equation is n dash a n, that is equal to under root n delta n dash n minus 1, and the second equation n dash a dagger n, and so forth. Okay, so this is the matrix elements. These are the operators which I can write in the form of matrix. Okay, so if I write this n dash a n in the form of, or operator a in the form of matrix, I'm writing like this: 0 a0 0 a1 etc. Okay, And look at this term, this is 0 and this is also 0, this is 1, this is 1, this is n, this is n. Okay, that means the n dash and n comes, when n dash and n comes, n dash and n will be equal, we will get the diagonal elements. Okay, for all operators, if n dash and n are equal, that elements are diagonal elements. Okay, then we will check what will happen if n dash will be equal to n. Okay, n dash will be equal to n. Okay, now n dash equal to n, that means this all are diagonal elements of different operators a dagger, x and p. And if n dash equal to n, then this n dash will become n. So that is equal to this is n and this is n minus 1. So delta n minus 1 equal to 0. Delta this will be under root n only when n equal to n minus 1. So this is equal to 0. Similarly, we are finding the diagonal elements of this different operators. That means this is n plus 1, that also equal to 0, and here it's n, and delta n minus 1, delta n plus 1, this will become 0, and here also last term npn equal to 0. That means the diagonal elements of this operators will become 0. That means these operators are not diagonal in the n representation. These operators are not diagonal in n representation. That means these operators will not commute with n. These operators will not commute with n. Especially this is not equal to 0. Okay, this will not commute, and the x operator like this a and a dagger, x and p operators will not commute with n. Okay. In previous class, we have derived energy eigenvalue of simple harmonic oscillator. Now I'm going to derive energy eigenfunctions in position space. Okay, let's start with the ground state of simple harmonic oscillator. Ground state of simple harmonic oscillator means where n equal to 0. Okay, now we are starting with the ground state. That is, we can represent that ground state A0 equal to 0. Okay, according to this equation, A0 is under root n kit n minus 1. Okay, so we will get that is equal to 0. This is the ground state of simple harmonic oscillator. In position representation, we have learned in the first chapter, in position representation, we can represent a wave function as x dash alpha. Okay, now we are applying that one. Here our ground state of simple harmonic oscillator is A0. That means our alpha is A0, and that is equal to x dash, and we know what is annihilation operator. This that is under root m omega over 2h cross x plus ip over m omega get 0 equal to 0. Okay, this is equal to 0 because A0 equal to 0. So the left side is equal to 0. That's why we got 0 here. Okay, now we are going to derive it, and that is, we can take this under root m omega over 2h cross outside, and x dash x0 plus x dash ip over m omega 0, and that is equal to 0. Okay, this m omega under root m omega over 2h cross will get cancelled because in the right side it's 0, and that implies x dash. If this operator operates on this x dash, we will get the eigenvalue x dash. Okay, that also we are familiar in the first chapter, wave function. Okay, so x dash 0 plus I over m omega x dash p0. Okay, this I over m omega getting outside, and here this x dash p0, that is equal to 0. Okay, that implies x dash. Look at this. This is x dash p0. X dash p0. In the first chapter, we have studied the momentum operator in position basis. The momentum operator in position basis, we got actually the momentum operator as minus ih cross dou over dou x dash. Okay, so the momentum operator in position space is minus ih cross dou by dou x dash, that we are applying here, and we will get that is I over m omega into ih cross dou by dou x dash, dou by dou x dash 0, x dash 0. Okay, so that is equal to 0. Okay, that implies x dash, we are taking this x dash 0 common, that is x dash plus h cross over m omega dou by dou x dash of x dash 0 equal to 0. Okay, and for this value, for h cross over m omega, we are putting h cross over x naught, we are putting x naught equal to under root h cross over m omega. So this we can represent as x naught square dou over dou x dash. Okay, and this will lead to this equation. This is a first order differential equation, dou by dou x dash of x dash 0 plus x dash square over x naught square x dash 0 equal to 0. Okay, let me consider this as psi naught. This as psi naught, a wave function, energy eigenfunction psi naught plus x dash over x naught square psi naught equal to 0. Okay, look at this. This is the first order differential equation. When I solve it, I'll get psi naught. That means x dash 0 equal to 1 over pi raised to 1 by 4 x naught raised to 1 by 2 e raised to minus 1 by 2 x dash over x naught square. This is the solution. This is the solution of this first order differential equation. Okay. And let me put this as equation 20. Equation 20, this is the ground state wave function of simple harmonic oscillator. And I'm going to, with a normalization constant, this is the normalization constant 1 over pi raised to 1 by 4 x naught raised to half. This is the normalization constant, and I'll give you the whole derivation of this one, how to derive the first order differential equation for the wave function, ground state wave function of the simple harmonic oscillator. Okay, in a paper. Okay, I don't have much time to explain that one. That's why it will take too much of time. So here I'm going to explain the physical significance of this ground state, the physical significance of this energy eigenfunction. Okay, if I'm considering an eigenfunction in position space, energy eigenfunction position space, this is the equation x dash alpha, and here I got this as x dash 0. Okay, this is the ground state energy eigenfunction of simple harmonic oscillator, and I can represent as psi naught. Okay, when I want to define the physical significance, I need to consider mod x dash alpha whole square dx dash. Okay, what it means? It means actually the probability of finding the particle to be in a narrow region dx dash. That's the meaning of this one. Okay, so when we are considering the wave function, ground state wave function of this simple harmonic oscillator, and we can represent the energy states like this. The minimum energy state is half h cross omega, and then 3 by 2 h cross omega, and then 5 by 2 h cross omega, and so on. Okay, so the particle is in ground state energy level. That means the particle have energy. The simple harmonic oscillator, when a particle is oscillating, a particle is executing simple harmonic oscillation, its energy is half h cross omega, because we are considering the ground state energy. Okay, so in ground state, the particle is oscillating with an energy half h cross omega. We need to find this particle executes simple harmonic oscillation about in position. So when we are considering a narrow region, dx dash. Okay, dx dash. We are considering a narrow region dx dash. Actually, if we are finding x dash 0 mod x dash 0 whole square dx dash means the probability of finding the particle in a narrow interval dx dash with energy half h cross omega, because this particle is in ground state and its energy is half h cross omega. Now by taking this equation, we have derived the energy eigenfunction and energy eigenfunction possession space. Now I am considering the mod square of this x dash 0 dx dash. That means this has the physical importance. Okay, this is just a function. This is just a wave function. When we are giving something, it will give out something. Okay, that's the importance of a function. This is a mathematical. This has the mathematical importance only. The physical significance of the mod square dx dash, the probability of finding this particle which executes simple harmonic oscillation in a narrow interval dx dash with energy half h cross omega, since it's in ground state. Since it's in ground state, it executes simple harmonic oscillation in ground state. That's the importance of energy eigenfunction. Okay.